Hello guys, welcome back. Today we're going to chat about pH and pOH. So we're going to get into a little bit of calculations in the solutions unit, right? So we're talking acids and bases and neutral substances as well. And now we're going to do some calculating. So I know you guys are probably comfortable with the pH scale because it's something that we see on a fairly common basis as consumers. So the pH scale, you may not realize what it actually stands for, the term pH. pH actually stands for power of hydrogen. And so what that scale is measuring is how concentrated your solution is with hydrogen ions, or more specifically hydronium ions. Now, one thing I do want to specify for you right now, or make very clear, is that we're now specifically talking about hydronium being the primary ion that creates, or that gives an acid its acidic properties. But I'll warn you that in the pH unit, or in the pH section, we tend to use the hydronium and the hydrogen ion kind of interchangeably and a little loosey-goosey. So don't let that confuse you. We still show reactions in terms of hydronium and such. But for pH, we simplify things and we just use our regular old Arrhenius, not necessarily our modified Arrhenius. Okay, it just simplifies life for us. So the pH scale basically looks most commonly at a range between 0 to 14. I have seen the pH scale before ranging between -1 and 15. So it is possible to end up with a pH that's in the negative scale. All that really tells you is that you've got an extremely high concentration of hydrogen ions. But generally for most of the things we'll be working with, you'll see 0 to 14. If you happen to see a negative value or something higher than 14, don't panic, it is possible. Okay. And the things to note on the pH scale is that the lower your pH, the more acidic your solution. The higher your pH, the more basic your solution. And if you're right smack dab in the middle, you've got a neutral solution. Okay. Now, note that we're measuring power of hydrogen. So as we move down, your concentration of hydrogen will increase because your solution is becoming more and more acidic. And so if the solution is becoming more acidic, it means there's more hydrogen ions floating in solution. If there's more concentration of hydrogen ions, that means the pH value goes down. So it's an inverse relationship. The pH scale gets lower as the concentration of hydrogen ions gets higher. And for a basic solution, as the pH goes up, the concentration of hydrogen ions goes down. Now, this may seem a little bit weird to you guys because you guys know that bases have hydroxide. So where is this hydrogen ion coming into play? And so I'll explain that momentarily. But the important thing to note is that the hydrogen ion that is present in a base is coming from the water solvent itself. And I'll show you how that happens. But every amount of distilled water or pure water is going to have a certain amount of hydrogen ions in it. Okay, so that's where the hydrogen comes in your basic solution, because the water itself carries hydrogen ions. So the backstory to why water has some hydrogen ions. Water undergoes something that's called auto-ionization of water. And basically what happens in a sample of pure water is that 2 out of every billion molecules will collide with enough force that one of those hydrogens actually gets bumped off of this molecule and it gets attached to the other water molecule. And in that process, by colliding hard enough that the hydrogen transfers, we end up producing 1 ion of hydronium and 1 ion of hydroxide. So that's for every 2 out of every billion molecules. And so that's why water, pure water itself, pure water carries some amount of hydronium in it, and it carries some amount of hydroxide. And the important thing to note is that the ratio between the hydronium and the hydroxide is equal. It's always a 1-to-1 ratio in pure water. So that ratio between the two is completely balanced. So when you make a solution, that solution is always going to have a balanced amount of hydronium and a balanced amount of hydroxide, because the water itself carries equal amounts of hydronium and hydroxide. And if you've got equal amounts of these two ions, that means that we have a neutral solution. If we have more hydronium, that means that we have an acidic solution. If we have more hydroxide, that means we've got a basic solution. And I've got a pretty good diagram down here for you to help you visualize that. So here's your pH scale. You'll see here at a neutral pH of 7, and I'm just going to make this maybe a little bit smaller so you can see it still. At a pH of 7, notice I've got my teeter-totter happening here. At a pH of 7, the concentration of hydroxide and the concentration of hydronium are completely balanced. They're completely equal. And that's why the pH is 7. It's neutral, since there's a balance between the hydronium and the hydroxide. If we increase the amount of hydronium and we cause the scale to dip toward the hydronium side, like we have here, then what happens is our solution starts becoming acidic. And the more hydronium we add to this side of the scale, the more acidic the solution becomes and the lower the pH gets. So on the left-hand side of our scale here, the side under 7, you're always going to have a greater concentration of hydronium in comparison to hydroxide. Remember that the hydroxide is there because there's hydroxide present in the water. If we do the reverse, and so we start again with our scale balanced, and now we start adding more and more hydroxide. So in this case, we're tipping the scales toward the hydroxide side, which means that we're making the solution more basic. So concentration of hydroxide is getting larger than concentration of hydronium, which means our pH is becoming greater than 7. And remember that this hydronium present in your base is coming from the water itself. Okay, this is another way that I like also representing that pH, balance between hydroxide and hydronium. So again, I'm using the hydrogen very loosey-goosey here. But I've got my Z here. On this side, pH is really, really low, so that means I've got a very large amount of hydrogen, or hydronium. And I've got a teeny tiny amount of hydroxide that comes from the water that's been mixed to make the solution. As I move to 7, the amounts between the hydronium and the hydroxide are equal. And as I move to a pH of 14, the hydroxide is way more in concentration than the hydronium that comes from the water. So two ways to look at that. Now the thing to note about pH is that it is an inverse relationship. So if you guys remember back to when we were doing Boyle's law in the gas unit, our Boyle's law graph was an inverse relationship, and the relationship looked a lot like this in terms of our line of best fit. So in this case here, we've got pH on the bottom, we've got acid, neutral, base on the bottom, and here we've got concentration of hydronium. So yes, we do have pH on the bottom here. We're manipulating the pH, and we're seeing how does the hydronium ion concentration change. And so as we move closer to the 0, meaning that our pH gets closer to 0, you'll notice that our line here, our line of best fit, spikes, right? So that means that the pH just skyrockets as you get closer to a pH of 0. As we get closer to a pH of 14, you'll notice that our line plummets and it gets closer and closer to a concentration of 0, right? So it's an inverse relationship, and this is a logarithmic relationship. pH in comparison to hydronium concentration is a logarithmic scale. And that's what we've got down here. And so this formula, pH equals negative log of the hydronium ion concentration, and this formula is something you need to remember. It will not be on your tests. It's something that you have to remember. Okay. And the other thing that you have to be aware of is that pH, you know, unfortunately or fortunately, now that you're finally getting your head wrapped around significant digits, pH actually carries its own significant digit rules that take a little bit of getting used to. And the deal with significant digits is that the number of digits in the concentration equals the number of decimal places in the pH. So the number of digits in your concentration equals the number of decimal places in your pH. So I've got an example here for you of a pH calculation. And we have a solution has a concentration of 1.0 times 10 to the negative 4 moles per liter. What is the pH? So pH is equal to negative log of the hydronium ion concentration, which means negative log of 1.0 times 10 to the negative 4. If we put this into our calculator, and this is what I'd like you to do right now, put this into your calculator and make sure you get an answer of 4, because every calculator is slightly different in how you input the values. So you need to make sure that you know how to use your calculator specifically so that you get the right answer. At this point, I would highly recommend that you have a calculator you work with constantly, and you don't switch around between your phone and your scientific calculator or a friend's calculator, because there's nothing worse than being on a test and trying to figure out how to use a calculator properly. So hopefully by this point you've got your pH of 4. The next thing is we have to figure out how many significant digits, right? So remember, the number of significant digits in our concentration is the number of decimal places in our pH. So this concentration has 2 significant digits, which means that our pH has to carry 2 decimal places. The 4 doesn't count because the 4 is represented by the exponent. And in this case, if you notice, generally the exponent on your concentration is going to be either bang on or pretty darn close to your pH. In this case, the exponent is bang on with our pH because we're dealing with a concentration of 1.0 times 10 to the negative 4. If this was something like 3.9 times 10 to the negative 4, we wouldn't be right on a pH of 4. We'd be somewhere close, but not right on. Okay. So the exponent represents the pH. So you can always look at your exponent and kind of get an idea of where you should be in terms of your pH answer. Now, that's to calculate pH. So you have to remember this formula. If we want to rearrange this formula in order to calculate concentration, because that's also a possibility. In this case, when we do our log, this is the logarithm to the base 10 that we're doing. So to do the inverse of the logarithm, we would take 10 to the negative pH. That would give us our concentration if we rearranged our pH formula, 10 to the negative pH. And you do have to remember this. So an example, kind of easy peasy example, nothing fancy, is if the pH is 12.598, what is the concentration of the hydronium? So we remember that concentration of hydronium is equal to 10 to the negative pH, which is 10 to the negative 12.598. Now notice that I've written here the number of decimal places. We've got 3 decimal places, and the reason I've put that there is because if our pH has 3 decimal places, that means that our answer, our final answer, needs to have 3 significant digits. So I put this into my calculator. I want you guys to do that as well. And you should get 2.52 times 10 to the negative 13 moles per liter. Notice that I've expressed my final answer to 3 significant digits because my pH has 3 decimal places. And remember I said that the exponent will generally be, the exponent represents the pH. So the exponent should be pretty darn close to what your pH value is. Notice I have an exponent of 13 and my pH is 12.598. So it's pretty close. The exponent always represents the pH. Okay. So that's for pH, and that's generally the scale that people are a little bit more comfortable with. The one that people haven't heard of very much and we don't use very often in terms of consumer products is pOH. Now, if pH measures power of hydrogen, pOH measures power of hydroxide. Okay. And the nice thing is that the formulas are identical because the only difference between pH and pOH is that the pOH is measuring the flip side of the pH scale. So remember that there's always OH and there's always hydronium in a solution because the water carries it, right? So the pH measures the opposite side. It measures the hydronium side of the solution. So because it measures the opposite side, the formula is identical. The only difference is that instead of measuring hydronium concentration, pOH focuses on hydroxide concentration. So the formula to calculate our pOH is negative log times hydroxide ion negative log of the hydroxide ion concentration. And if we rearrange that to solve for hydroxide ion concentration, we get 10 to the negative pOH. Okay. So let me show you when I was saying the flip side of the pH scale, what I mean. So our pH scale goes from 0 to 14. Typically speaking, when we talk about anything pH less than 7, we're talking acid. Generally, we can say that anything below a pH of 3 is a strong acid. Anything between 3 to 7 is a weak acid. It could also be, I have dilute here. It could be a weak acid, but it could also be a diluted concentrated acid. And here, I'm going to add this in here for you guys, or a dilute strong acid. And this is referring to weak acid. It could be a strong acid if the pH is below 3, or it could be a concentrated weak acid. Because if we concentrate the weak acid, the pH goes down as well. Now, if we have a pH of 7 to 10, generally say this is a weak base. So this could be a weak base, or it could be a diluted strong base. And pH of 10 to 14, this could be a strong base or a concentrated weak base. And we'll talk a little bit more about concentrated versus weak in another lesson. But keep that in the back of your head. You can take something that's very, very weak, and if you just evaporate the water away from it, the concentration will go up. And so you can actually make the pH get stronger if the concentration goes up. For the pOH, it's the flip side. So a pOH of 0, between 0 and 7, that's measuring a base. And a pOH of anything above 7 is measuring a strong acid. Okay, so the range is still the same. It's still 0 to 14. It's just that anything below 7 on the pOH scale means that you've got a very high concentration of hydroxide. So that means base. Anything with a pH higher than 7 on the pOH scale means you've got a very weak concentration of hydroxide. So that means acid. And then the same thing goes here. If you've got a pOH of 0 to 3, this could be a strong base, or it could be a concentrated weak base. If we've got a pOH of 3 to 7, this could be a weak base or a diluted strong base. If we've got a pOH of 7 to 10, this could be a weak acid or a diluted strong acid. And if you've got a pOH of 10 to 14, this could be a strong acid or a concentrated weak acid. So take a little time with that because there's a lot to digest right there. So take a little bit of time, think about that, pause the video, and try to organize that in your head. Now, the other thing I'm going to show you is this little roadmap. Okay, and this little roadmap is going to be really important for you guys. And specifically what's going to be important for you is this section here, this under section here. This is what for you guys is going to be important right there. This portion up here that I've circled in green, this portion is important, and you're welcome to use it at this point, but you're not really going to delve into this section until you get into the next level. Okay. So what I've done here is I've put together, I guess, the roadmap for how you would work between the two scales. So if you're given concentration of hydronium and you want to go from concentration to pH, you're going to use negative log of the hydronium ion concentration. To keep going from pH to pOH, we're going to do 14 is equal to pH plus pOH. And then to keep going to concentration of hydroxide, we'll do 10 to the negative pOH. If we want to go the reverse way, so we start with hydroxide ion concentration, we can solve for pOH using negative log of the hydroxide ion concentration. To get to the pH scale, we know that 14 is equal to pH plus pOH. And then to get to the concentration of the hydronium, we would use 10 to the negative pH. So that's your roadmap. Now we're going to do, I've got a bunch of examples for you guys here that we're going to do right now. So this one tells us a sample of sulfuric acid has a pH of, let me see if I can get rid of this thing. I don't know why it's there. It has a concentration of, it has a pH of 0.753. So this is really acidic, right? Super acidic is what you should be thinking right now. Calculate the concentration of the hydroxide. Now, some people would be like, whoa, hang on a second, we're dealing with an acid. How is there hydroxide in there? Don't forget that the hydroxide comes because we had to mix this solute with water, and the water carries hydroxide inherently in it. So that means that on our roadmap, we've been given pH. So on our roadmap, we're starting right here. And we need to get up here to concentration of hydroxide. So I'm going to get on the blue line here to get to pOH, and then I'm going to follow that blue line up to the concentration of the hydroxide. So step 1 is 14 is equal to pH plus pOH. And I need to solve for pOH. So pOH is equal to 14 minus pH, and that's 14 minus 0.753, which gives me 13.247. Now I'm going to hold on to all my digits, don't round anything until the very, very end. Now I'm here at the pOH scale. I have to get up to concentration of hydroxide, which is 10 to the negative pOH. So 10 to the negative pOH, I just found out pOH is 10 to the negative 13.247. Put that in my calculator and I get that the concentration of the hydroxide is 5.66 times 10 to the negative 14 moles per liter. Okay, because that my pOH has 3 decimal places, that means I'm going to round my concentration to 3 significant digits. Okay, so that's the first example. The second example is slightly more complex because there's one extra step here. So we have student dissolved 3.00 grams of hydrogen nitrate solid into 250 milliliters of water, and we want to know what is the pH and the pOH of the solution. So this is slightly more complex because not only are we trying to figure out pH and pOH, but holy moly, now we have to go back to the solutions unit and we have to figure out what's the concentration of this. Okay, so there's a whole lot of stuff happening in this two-sentence question. So we'll take our 3.00 grams. Remember, if they give you grams, you're going to have to solve for grams per mole. So I solve for molar mass of HNO3, which is 63.02. I'll put the 63.02 on the bottom of the division and the moles on the top. That gets rid of my grams. They told me 250 milliliters, so I'm going to put that into liters because I want concentration. Moles is on the top, liters is on the bottom. I multiply and divide through, and I get 0.190 moles per liter. That's the concentration of my entire solution. Now, here's the kicker. This is the concentration of the HNO3. Fantastic. But unfortunately, that doesn't help us because if you look back at our formulas, whoa, too far. If you look back at our formulas, all of our formulas deal with log of concentration of hydronium ion or hydroxide ion. In no spot here does it say anything about concentration of solution. So that's the second part that makes it slightly complex because you have to think back to our concentration of ions section from the previous unit. So remember that if we have HNO3, we're keeping this simple. We're going back to our original Arrhenius definition. So we're not going to undergo hydrolysis here. All I'm interested in is ionizing this particular HNO3 aqueous. It's going to ionize into hydrogen ion and nitrate ion. I know the concentration of the HNO3 is 0.190 moles per liter. I want to figure out what's the concentration of the hydrogen because that's what I need to work with pH. So this is a 1-to-1 ratio, which means that my concentration of my hydrogen ion is 0.190 moles per liter. Now I can do pH. So remember, I'm using hydronium and hydrogen interchangeably in this section. So I know pH is negative log of the hydronium ion concentration. And I just figured out that my hydronium ion concentration is 0.190 moles per liter. If I take the negative log of that, I get 0.721, right? And because my significant digits in my concentration is 3 significant digits, my significant digits in my pH is going to have 3 decimal places. Now to figure out pOH, I just take 14 minus pH, and I got 13.279. Okay, so again, 3 decimal places. That's the second example, slightly more complex. In this example, again, a little bit complex, 350 milliliters of HCl gas is bubbled into a 750 milliliter sample of water at SATP. Oh man, gases, right? SATP, I need to remember 1 mole is equal to 24.8 liters. Find the pH of the solution. So I want to figure out, I have 350 milliliters HCl bubbled into this solution. So 350 milliliters times 1 mole over 24.8 liters. This means I have 0.0141129 moles of HCl. That's how many moles were bubbled into my solution, because they gave me a volume of HCl. Now I figure out, well, what's the concentration of the HCl? So I'm going to take this number of moles. I know that I made a solution with 750 milliliters of water. So I'll put moles on the top, liters on the bottom, liters of solution. And I get 0.0188172 molar solution. Again, it's a 1-to-1 ratio. So the concentration of the solution doesn't help me. And what I need to know is what's the concentration of the hydronium. And remember, I'm using these terms interchangeably. And we're just taking regular old Arrhenius here, just to figure out what's the ratio between the hydrogen and the solute. So it's a 1-to-1 ratio, which means that the hydronium ion concentration is equal to the hydrochloric acid concentration. And so pH is equal to negative log of hydronium, negative log of 0.0188172 moles per liter, and we get 1.725 is our pH. And I go back and look at what was my significant digits. I had 3 here from the volumes, which means that my concentration, theoretically, if I'd stopped there, would have had 3 significant digits. If my concentration had 3 significant digits, my pH should have 3 decimal places. Okay, so that's another challenging one as well. Now this is where everything's kind of coming together, right, and being able to pull it all together. Last one I think I've got for you here is, what is the pH of a calcium hydroxide solution if a student dissolved 1.85 grams of calcium hydroxide solid to make a 500 milliliter solution? So 1.85 grams molar mass of calcium hydroxide and a 500 milliliter solution. So we get 0.0499 moles per liter. That's of the calcium hydroxide, the entire solution. So I have to figure out, because I can't do pH, I can't do pOH with concentration of solution. I need concentration of ions. So this is going to dissociate into a calcium ion and 2 hydroxide ions. I know my concentration of the solution is 0.0499 moles per liter. It's a 1-to-2 ratio, right? So that means the concentration of the hydroxide is double, 0.09986 moles per liter. Once I've got that concentration of the hydroxide, now I can calculate pOH. So pOH is going to be negative log of 0.09986 moles per liter. That gives me 1.001 as my pOH. And then my pH is 14 minus the pOH. So I get 12.999. And I keep the 3 decimal places because my smallest number of significant digits here was 3, which means that if I had stopped at my concentration would have been 3 digits. Okay, so that means that my significant digits for pH, for pH is 3 decimal places. So that's it, guys. That's pH and pOH in a bit of a nutshell for you. There's a ton of stuff happening there, and you know what? Their most simple pH calculations are relatively easy, but they can get quite involved. So there's a lot of practice that we're going to work through. Unfortunately, we only have a Friday lesson for it, but before we go on break. But we will do some practice together in class. Please come to class with any questions you might have. And then we will carry on when we get back from break. I hope you guys are doing well. Take care, and we'll chat with you very, very soon.